In the early universe, there was inflation, which is the rapidly expansions of the universe. Such inflation theory is introduces to explain the horizon problem or brightness problem. And after the inflations, the universe got into the radiation dominant era, so that we need to end the inflation, and that this moment is called the heating, because the energy is deposited in the inflaton, the scalar field which is makes the inflations. But the such energy deposited in inflatons now the transits to the other standard model structures, so the universe becomes a radiation dominant, and this is called heating, because the standard model species is again, and this conversion stages from the inflaton to the standard model structures can occur by the decays of the inflaton, and eventually the raising the entropy density and the temperatures of the universe. We can quantitatively write this inflaton decay in terms of the decay rate gamma, and the energy transfer from the inflaton pi to the radiation component R can be written like this coupled equation, where the rho represents the energy density of the inflatons and the radiations respectively, and H is the Hubble light, which comes in from the expansion effect, and the coefficients for the inflaton and the radiations are different due to the different scaling behavior, and the W is the effective equation of states for the inflaton. And in the right hand side, the decay rates of the inflaton transfers between the scalar field pi and the radiation term. And when the inflaton decay rate has a similar order to the Hubble scale, then the rating is now the activities, and the radiation density can be written by the temperatures by using the equilibrium thermodynamics, and by inserting this in the Hubble parameters by the Boltzmann equations, then we can obtain the temperatures for the heating, which satisfies the Hubble light, and the decay light becomes comparable. So the heating temperatures can be written in terms of the inflaton decay light, and the other coefficient G star, the effective the numbers of the relative species, also depends on the temperature things and the Planck mass, which comes from the coefficients of the Boltzmann equations. But such a weighting is quite limited and restricted, because such a weighting only occurs by the perturbative frictions with the decay lights of the inflaton. So it is too slow and incomplete, so the inflaton might lose energy during their decay. So we need to make the immediately rapid decay of the inflaton to make the energy transfer from the inflaton to the standard model species as a complete version. And such a rapid decay can be possible by the large amplitudes of the scalar fields and the coherent oscillating background. And if this inflaton oscillating inflaton fields are coupled to the other fields, then they get the effective mass and the frequencies with the periodicity in the time, and this makes the non-perturbative particle productions. This is called preheating. And today I will talk about the preheatings after the inflations with the phenomenon of the parametric resonance as advanced versions of the rating. So we can consider the following Lagrangians. The simple example is the additional scalar chi is coupled to the inflaton field pi as the quartic term, pi squares and the chi squares, and the g here is this is coupling. Then the inflaton field pi is oscillated around is the minimums of the potentials, like that. And if we assume that this pi get how many oscillations, then the mass term of the chi gets the effective time dependent term, whereas m chi joules is the bare mass term under this Potala coupling between the inflaton pi and the additional scalar chi induce the time dependence term. By Fourier transformation, the frequency sort of this scalar chi can be written by the following form, where the this is the dispersion relations from the energy, momentum, and the mass, where the scale factors are the divided for the momentum part. So the this frequency determine the specific k mode, and due to the time dependent behaviors of the mass term, also the frequency oscillates through the time. So periodically varying frequencies makes a non-adiabatic limit, which is the equivalently written as the changes of the frequency is larger than its magnitude in the dimensionless setup. And such in a non-adiabatic limit, the particle numbers are not conserved. The particle numbers breaks down, and the rapid reproductions of the particle can occur. And such a phenomena is called the parametric resonance. Not only the cosmology, but also in the classical mechanics regime, such a parametric resonance can be possible when the frequency has time-dependent behavior. And this eventually makes the rapidly growth of the field fluctuations, and the occupation numbers become extremely large. And especially with such a rapid case, the energy transfer can occur very well compared with the typical reading scenario. So the energy transfer can be occurs completely. So now let's focus on how the parametric resonances are occurring in the mathematical regime. So let's consider that the mode equations satisfy the following differential equations with time-dependent frequencies, and they have some periodicity with specific periods capital T. And assumes that the inflaton field has approximately how many oscillations behaviors with amplitude capital pi, and the periodicity is with the oscillating frequency of its mass. And then we can expand this the time-dependent frequencies, and the last the scale factors here for simplicity. Then we can write again the time-dependent mass term of the chi with the full expansion of the how many oscillations term. And by changing the variable, let's the m pi t's defines as a jet new time variable, and the chi k to the xk, and we can obtain the new forms of the equations. This is called the Mateiu's form, where the q is defined by the ratio between the coupling and times amplitudes and the mass, and the ak that includes the frequencies and its bare mass term. And now this coefficient is periodic in the jet, and by the Floquet theory, the solutions of this equation has the following identity, where the solution xk of the jet has the exponent of the mu k jet times the functions of the pk of the jet, where the pk of the jet has a periodicity with the pi. here's the mu k is called the Floquet exponent, and when the real number parts of this Floquet exponent mu k is the positive, then this means that the solutions of the xk such that has exponent behavior. But if the real part is negatives, and all the if there is some imaginary part, then it shows the decreasing the exponential behavior, sort of oscillating behavior. So we want to find some specific instability bounds of these Mateiu's equations, was the block and exponent mu k has a positive real part, and this region is called the instability bound over some parameter space ak and the q. So inside of these parameter regions, the solution xk, the modes grows exponentially, and we can introduce the occupation number for each time as the following form, with chi k and chi k dot can be obtained by the solutions of the xk, and eventually the exponential growth behavior of the solution xk makes the occupation numbers also grows over the time. So and such exponential growth occurs until the nonlinear epoch, like the back reactions between the pi and the chi, or rescattering from the perturbative epochs, the insults, the such instability is unstable exponential growth that occurs. But if such a nonlinear epochs are getting sized, then the exponential growth stops, and the parameters get outside of the instability bound. So we can draw some specific parameter versions of the instability bounds. There are two versions. The first one is a narrow resonance, and the second one is a broad resonance. So there are two parameter space here, and if the maybe the q in the x-axis and the ak in the y-axis, and if the q is smaller than the 1, this is called the narrow resonance. In these regions, there are specific instability regions around some centers where the ak is the power of the integer. So ak equal to the 1, equal to the 4, 9, 16. Around this number, there are some specific instability bound here. And this region is quite thin. For example, if we consider ak around to the 1, this bound is approximately the inside of the 1 minus q to the 1 plus q, where the q is extremely small. And we can evaluate the mu k, because of this mu k, the block count exponent is a function of the parameter ak and the q. So for the dispersed band, whereas ak is around the 1, the functions for the mu k in terms of the q and ak is written like that. Also, there are another version where the q is larger than the 1. There is a very broad resonance. Instability band is very wide, so the many modes can satisfy the positive real part of the mu k. So the amplifications in these versions is quite efficient compared to the narrow versions. But eventually, the such resonance will stop by the nonlinear effect, like the back reactions or the rescattering. Such a Floquet theory is linear because we assume that the background built inflaton pi has harmonic oscillation behavior, but because the Lagrangians contains the totality between the background built pi and the additional scalar chi, so if the build values of the chi's changes together, then also the mass term of the pi also changes over the time. This means that in harmonic oscillations terms, this m, the mass term of this scalar field pi has also oscillating the behavior. So the by this back reactions reflex, it might the parameter space of the AK and the Q can get outstripped from the instability band, and the eventual resonance will be shut off. So, as an example, if we can write the background field pi as the Belgian pi bar and the little fluctuations the delta pi, then we can expand this the homogeneous inflaton mode as equation of motion term. But the background field mass also got the oscillating mass term, which is contributed from the additional scalar chi. So that this makes the again by the back reactions the frequencies of the chi field also changes over the time. So this make the because the parameters AKs are defined as with the this m pi square. So the if the m pi square that changes, for example, if the m pi goes to large, then this makes AKs become small. So the parameter AK might shift from the instability band, and the resonance behaviors might be stopped. The practical criteria for the shut off can be written by this form. There are two contributions in the effective mass of the background field pi. The first one is the Belgium M, and the second one is the contributions from the chi field. And when this contribution from the chi field is rather than the bare mass term, then the effective masses of the pi changes over the time, so that it makes the shadow. And also if the Q, the other parameters, is the Q is smaller than the 1, order of the 1, then it goes to the narrow resonance band. And it's quite difficult to satisfy the resonance condition, or other words in the instability band. So the Floquet exponent in k is the strongly surplused, and no longer there is no exponential close in here. So eventually the resonance becomes stop. And also we can realize it again. Okay, this is the explanations for why the Q effective decreasing here. So here's the Q that defines it as the G squared pi squared over m pi squared. So if the m pi squared is large, then the Q becomes small. So if the effective mass of the pi is large, so Q can be the smaller than the order of the 1. This eventually the parameters go to the narrow resonance bound, and this makes the exponential amplifications that becomes a stop. The other effects to stop the resonance is the least scattering, so by considering the some specific perturbative process. Now the chi particle that produces very much with exponential growth, and they are scattered with themselves, like as a chi scattering, or the chi can also scatter to the pi field, the background field, and this can produce the inflaton fluctuations, delta pi. And due to this delta pi, the non-linear effects are inserted. So how can we deal with this inflaton's fluctuations? The time derivatives of the number density can be written by the two terms. The first term represents the resonant amplifications, The second one is the contributions from the some specific scattering or collisions. And when the second the collision terms becomes comparable to the first one, then the evolutions that described by the nonlinear scattering, and now the parametric resonance box becomes small. So so we talk about some theoretical and some theoretical point of view that is preheating through the parametric resonance with the specific equations and their solutions. Now I will talk about the very brief remarks on the phenomenological observable. The observable outcomes of the preheating scenario is the quite modality functions, but there are quite common things. The first one is this is can make the stochastic gravitational wave background by the inflaton decay and some specific signal like the non-Gaussianity or Isaac-Barthes perturbations or the topological debugs can be possible. And also the preheating can be the good scenario to produce the dark matters in the non-thermal scenario, and also can make some impacts on the Barron symmetry like the Barrow-Jones model. And already I mentioned the exhaustive gravitational wave, Isaac-Barthes perturbation or topological debugs can constrain some specific preheatings from the past. So today we talk about the preheating scenarios with the parametric resonance with the time-dependent frequency. This can make the particle productions with exponential growth in the specific instability bands in the Panto space. This preheating is broadly proposed by the Goffman and Stravinsky in the 1990s with the non-perturbed effects to make the efficiency instabilities from the energy transfer from the inflaton to the radiations past. The inflatons because oscillated current over this around this the minimum sort of the potentials, and this makes the effective time dependence effective mass and the frequencies, and eventually it goes to the most go to the parametric resonance, and their occupation numbers grows exponentially. So such a total coupling between the background fields and the additional field can make the effective time-dependent mass and broad resonance regime is possible.